Hello and welcome to the webinar of Würth Elektronik ISOs. My name is Eleni Anastasatis and I will moderate the webinar today. We are very pleased that you took the time to participate in our webinar. Our speaker today is our development engineer Laurent Völkel. He will hold today's webinar on how do I select the right inductor for a DC-DC converter design and also answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you can't ask us questions via your microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. Please also indicate the slide number from the presentation in your question, so that we can easily relate your question. The slide number is located in the right corner and top of the presentation. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 15 minutes in addition scheduled for this. After the webinar has finished, you will find the entire recording a few hours later on our Ask Laurent website. And now I'm giving directly to our speaker Laurent Völkel, and I wish you an exciting webinar.
Hello everybody, my name is Laurent Völkel and thank you for Eleni for this excellent nice introduction. Well, today I will talk about how to calculate the right inductors for a DC-DC converter. Well, there are many questions when you are choosing the right power inductor. If you want to know about inductor, where are the losses, where are the core losses, copper losses. But before I would talk about a little bit about permeability and what is the effect of air gap, because the air gap is the part where we are storing the energy, how are inductors designed, and how to calculate the right value for a buck, boost, or even SEPI converter. And on the end, I have some EMC recommendation because, of course, if you're making a DC-DC converter, you don't want to fail on the EMC test, and that's the reason why I just give some idea maybe and some additional idea how to solve some EMC problem. Well, first of all, when you choose an inductor, you have many possibility between surface mount or through-hole technology, and even by surface mount, you can have different construction package. What is the right one? You have to decide, or the inductor will be small or too big because of the construction. But not only just the package is important, it's also important when you're choosing an inductor, which current you have to carry through the inductors. And then if you talk about current, which current? Rated current, saturation current. The next problem is, according to the efficiency, you have to keep the low DC resistance, then it should be temperature stable. Of course, should not affect in a negative form the EMC. It should be small, and all these are many questions for choosing a power inductor. Let me talk about few words about electromagnetism and physics. You can see here the Maxwell equation, and please believe me, I will not go through now to the Maxwell equation and squeeze you and scare you just with the equation that was actually just made for a joke. But honestly, you should know about that. The most important thing is when you're powering a copper wire, just to remember in the direction where your current is flowing, you remember the right-hand rule. If you apply your thumb to the direction of the current and you put your another forefinger above the wire, you will have a magnetic field. This magnetic field is directly proportional to the current and indirect proportional to the distance. It means if you are put more and more wires to the core, you can increase the number of turns this magnetic field. But it's very funny that we can realize that the magnetic field depends on the geometrics, depends on number of turns on the current, but not from material. And that means it's very funny that if I apply a ferromagnetic material above conductor above the wire and I leave flow a current, I can say in the middle of this core in a certain distance and the same current which is going also out of the core the same distance, I can assume that I have the same magnetic field. It must be real because this is the formula giving and I trust that. But how about the magnetic induction? It's the same as well? Just think about that. It could be different because air is bad magnetic conductive. As soon you apply a ferromagnetic material into the magnetic field, this magnetic field will bend. It will take the easier way to couple through. In the air choke, you will describe the induction formula B. It is mu 0 multiplied by H. Mu 0 is a vacuum permeability and mu r is 1. It's a wonderful, nice formula because if you apply more current to the wire, you have more H, automatically you will have a more B. It means you have a nice linear function. The problem begins when you have a sintered core material where you have to consider this mu r initial permeability or relative permeability because this is quite a dependent parameter. A special is depending when you are gluing your package your electronics and you use kind of hard gluing stuff, you may assume that the inductor will be the same like in before you glued, and this potting material, if it's too hard, it could occur something like a pressure to the inductance core. And you can see here this is a measurement made by our laboratory. From the 100% of the inductance value by 200 Newton, it will drop to 70%. So you have 30% losses only just because of the pressure, without current, without anything else, just because of the pressure. You have to consider that the permeability is very sensitive by sintered material to pressure. Additionally, you have to consider that are many different materials used to build the inductance. You can use iron powder, nickel zinc, manganese zinc, or even nanocrystalline core. A typical iron powder have a permeability up to 150, a nickel zinc reach 1,500, and manganese zinc you can reach 20,000. All these different materials are used to build some inductance. How to measure the permeability? Well, this is not so trivial because you need a magnetic analyzer. We are using an impedance analyzer actually from the company Keysight, former Agilent, former HP, and you have to use a special calibration jig for each core size, and then you apply a frequency. We are scanning from 1 megahertz to 1 gigahertz. We could do from 10 kilohertz to 3 gigahertz, but this is the area where we are scanning for characterizing the cores. And you can see that the impedance is actually a calculated value of root mean square of R square and XL square. XL, it is the impedance reactance, and R is the losses, the resistive part of this. Well, it's not so easy to measure it, and assembly to build that by yourself, it's almost difficult, and if you buy these instruments, it's a lot of money, believe me. If you don't build inductance, you will not need to do this by yourself. It is important to know this different core material because if you want to build a DC-DC converter and your switching frequency is roughly maximum 150 kilohertz, then you can use iron powder core, manganese zinc core, or even nickel zinc cores. As soon you are choosing new ICs for the new technology, which is the minimum switching frequency around about 500 kilohertz, and you still use the iron powder core, you will see at 500 kilohertz you will have less than 50% efficiency. And even if you have just 200 milliamp, just a small current output, and you will decide for a 5 amp big inductor, you will see that this inductor will start running hot, not because of the copper losses, because of the core losses. 500 kilohertz need a manganese zinc core or nickel zinc core. But manganese zinc has also his limits. Above 1-2 megahertz start to be very lossy, and absolutely at 5 megahertz I start to use a nickel zinc core. For DC-DC switching frequency you can go up to 10 megahertz with nickel zinc core. Even 20 megahertz would be possible, but honestly I don't imagine that one of you did build already a 10 megahertz DC-DC converter. Even today is possible. You can buy ICs which are capable to be switched by 10 megahertz. Myself, I make a small test, and I took an application board, a demo board, and I tried to see how it works, the DC-DC converter 10 megahertz. I was really fascinated about the size, how small you can build a DC-DC converter. With 10 megahertz you can reach an 1 centimeter scale excellent DC-DC converter, but yeah, it's a high frequency, honestly. First of all, when you have to take care for the sintering material, it is that the permeability is not only pressure dependent, it's also temperature dependent. When you qualify your product for industrial standard temperature like minus 40 degree to plus 85 degree, you will see that in ambient room temperature 23 degrees Celsius, you may have a permeability of 600 something. If you are going to the climatic chamber and cool down your device, your permeability will be something like 500. When you go up to 85 degrees Celsius, ambient temperature, you may have almost 800. So you can see this drifting of the permeability. It's influence your inductance. Remember, the inductance may have a tolerance of 10%, plus minus 10%, but this is on 10% tolerance on ambient temperature. You must take in consideration also this drifting of the temperature in the climatic chamber. So it could be minus 20 or even plus 15 above this room ambient temperature. Especially when you are operating in very high ambient temperature, then you have to take care that at a certain point above, like here, above 150 degree, the ferrite material reach his Curie temperature. It's not any more ferromagnetic, it's paramagnetic, and the mu R will drop to 1, not to 0, it will drop to 1. Doesn't matter how high was this temperature, doesn't matter how long you was outside of Curie temperature, when you cool down, it will be back. Now, with different air gaps, you can increase in some way the saturation point of the inductance. Every manufacturer of inductance play with this kind of air gaps into the inductance to have a higher saturation point and to keep the inductance small. Of course, small inductance like here, this bobbin core or this rod core inductance have an infinite air gap. By the shielded one, we are placing these air gaps between the shielding ring and the inside bobbin core. For the toroidal core, we are using a kind of distributed air gap like when you're choosing something like an iron powder core. This BH curve, if you see the material curve here by zero air gap, you may have a very, very fast saturation, which is not so good for a DC-DC current converter storage inductance. And applying an air gap to this core material, we extend the point of the saturation and of course about the permeability, because when we introduce this air gap into the core, the permeability it's dropping, and you have to consider that you will need to reach a semi-inductance value with a few copper turns of wire more. But what we want to reach always is a higher saturation point with not so much losing the permeability. Here is a comparison. You can see three different cores with three different inductors with two different core material. One of this is nickel zinc material, which is an unshielded one. You can see the saturation. This is inductance versus current curve. You can see here the saturation point of this unshielded bobbin core inductance is something like 3M, and as soon you put a shielding ring around him, his saturation point will be something like 1.7 M. It will saturate much faster. It's a shielded, it's good for EMI, but saturation point is faster. What you can do, it is if you use this kind of MAP inductance, which has a special alloy with a distributed air gap, it's still shielded and still have a linear saturation because it doesn't have a dedicated air gap, which can be very easy saturated. That is what we are playing like when we're manufacturing different inductance shapes and materials. Now, if you talk about switched mode power supplies, let me talk about first about the buck converter. The buck converter, in the first step, you can consider like a LC filter. You apply a rectangle signal to this LC filter and you're expecting a DC voltage on the output. Well, the problem is that the world is not so nice like we imagine and we dream. If you apply a rectangle signal to this LC, it will reflect a noise. And for this noise, you will need to put something like a ripple capacity on an input to try to filter out this reflected noise. Then additional, the word is not perfect, like I told you, and you have some parasitics on the input of this DC-DC converter. You have some wires, you have some PCB tracks, and if you have a load change on the output, maybe it will react not fast enough because the current doesn't flow enough fast, so you will need a bulk capacity on the input. This is your actually the input capacity. And then you can charge and discharge the energy from here and compensate this kind of load change. Well, a buck converter definition, it is that the input current is always less than the output current. So it means we have two stages. We have one stage switch closed and one stage switch open in a DC-DC converter. First, we charge the inductance, and then when we are open the switch, we discharge this inductance, and it means the source for the output will be the wall current discharging the inductance. So it means we are charging and discharging on an inductance, so we will have an inductance E max and you have an E minimum, and this change between input and output, switch on, switch off, it will be the ripple current. With this simplified formula, you can calculate already the ripple current, the output current, switching frequency, the input-output rapport, and a duty cycle. You can calculate the inductance value. You can see on this formula that if you increase the inductance value, automatically the ripple current will go down by the same condition. If you decrease the inductance value, automatically the ripple current goes up by constant switching frequency and constant E out. So in this case, you can play with this different inductance value to see if you have enough ripple or if you have too much ripple. You can consider that in choosing the right inductance value. By a boost converter, the topology is a little bit different. We have always the output voltage higher like the input voltage. Again, we have these two stages, switch closed, switch open, but this time it's a little bit different because the current to the inductance is always there. When a switch is closed, I charge the inductance. When a switch is open, I put the inductance current and in serial with the source, and I supply to the inductance again current. So the inductance will be always floated with current. This is the difference to the buck converter. Now, if you consider this inductance current, it means the inductance current will be always higher like the output current from your DC-DC converter. Again, with the simplified formula, you can calculate the inductance value for your DC-DC converter, and the same rule, smaller inductance, automatically much higher ripple, higher inductance value, automatically smaller ripple current. A good approach for a ripple current, I will say something between 20% minimum and 40% maximum. It's a good challenge for building a DC-DC converter. If you go less than 10% ripple current by the inductance, it will be the problem that you will not magnetize and not demagnetize enough. You will not have a nice BH loop into the inductance where the inductance can supply current. If you go higher like 50% ripple, you may have again the problem that you may have a major losses by magnetizing, demagnetizing, these eddy current losses, all these different fringing effect, skin effect, proximity effect. You will have a too high AC losses into the core and the inductance, and a good approach is, I would say, 40% to set up for a good efficiency and a good selection of the inductance. Well, depends now of when you're chasing a higher efficiency, you may have to consider that until approximately 1 amp, you may have some constant losses. The IC himself needs some current, some additional losses from the filter and so on. Above 1 amp and 5 amp, you may have to consider the switching losses and core losses will be dominant. By higher current like output current like 5 amp, you have to focus on the copper losses and RDS on losses because that will be your dominancy for reaching and improving a higher efficiency. How to select an inductor, how to parameter these inductors? Well, I will give you here a small example for a buck converter. We have an input voltage of 24 volt. Go down to 5 volt, 2 amp output current, 535 kilohertz switching, and there are some constant voltage switch and the forward voltage on the diode. And if you consider this formula with a 40% ripple current, you may have a peak current of 2.4 amp into the inductance, and the inductance value will be something like, I would say, 10 microhenry. Now you choose a 10 microhenry inductance according to the data sheet. You have to take care that in data sheet always you will have the test condition. It's normally always different like your switching frequency. This value of 10 microhenry, it is plus minus 20% tolerance measured by 1 kilohertz. It's always need a good calibrated LCR meter to measure that. The next point is that the rated current. The rated current, it is definition delta T 40 Kelvin. It means a self-heating of 40 Kelvin above the ambient temperature if you apply a 7.1 amp. So if you're applying to this component, inductor, 7.1 amp, he will be always higher with 40 degrees Celsius like the ambient temperature. That's the own 40 Kelvin self-heating. And now it's also a trap how to measure this, because if you measure the semi-inductance with 9 amp, and you will see that if you're using a huge clamp which have a good thermal conductivity, you may have only just 30 Kelvin. If you use some smaller clamps and not so good thermal conductive 35 clamp, we are measuring in a real condition soldered on a PCB with no heat sink, with no airflow, just to be sure that this is the inductance who making in fact this self-heating, which is 40 Kelvin. So you can lie by yourself if you're doing in such measurement tips. So it's not so, I would say, not so honest if you measure in that way. We are measuring with a no heat sink and no temperature transmission somewhere, that the inductance really measured with the infrared thermal camera. Now, for the inductance safe operation area, I would say I will choose my inductance always in this area where the inductance versus current will not drop. In the linear area, in this green box, it's almost the best thing. As soon the inductance drops 10% from his initial value, the critical operation area is start to be valid. So in this area, it depends if you not have enough space to put a bigger inductors or somewhere, but pay attention, this is also temperature influence. Sometimes it could be that the point is here, and sometimes this point is already here. So if you're applying a current of 10 amp and you consider in room ambient condition that you have a 30% saturation still working, you have to take care when you apply this current and also have a hot ambient temperature, because that curve can drift. The red area, this red box, it's a total saturation area. I would never recommend to use in this area inductance, because it's total crazy and will be not be satisfactory for the function. On the left picture, you can see this is a current clamp measured on the inductance leg. If you measure this current by the current clamp with the scope and you see exactly this current, that's the nice operation function of the inductance, how should be work. As soon you see this on your scope with the current clamp, that's the sign that your inductor start to be saturated and it will be not work in a satisfactory, I would say, area, and it will be not be efficient enough, and you will have anyway a lot of EMI problem additional because of this high peaks. That's the sign that the inductor are start to be saturated. How to measure the saturation current? Well, this is also not so easy setup. We are using that kind of Wanker measurement in instruments where we can apply a DC bias load, and as soon this inductance of 10 microhenry passing 10.5 amp DC current through him, his inductance will drop from 10 microhenry to 9 microhenry. It means 10% drop, and we say stop to use above this current because the inductance start to be saturated. I'm sorry to inform you that is not existing a standard to declare this saturation current. Every manufacturer uses a different point, and that's the reason why you can have sometimes 10% saturation, sometimes 20% or 30% saturation. A good engineering, it is by 10% drop to be defined a saturation current, and above this, it makes almost no sense to use it. How to select the inductance for the current? I would say for the buck converter, the output current of your DC-DC converter is the maximum current which is passing the RMS on your inductance, because the inductance himself, it is supplied as current and should be not saturated at all at this level, should be not running hot. And a boost converter, I will use anyway this formula for calculating the current which is passing the inductor, and definitely at this current, the inductance saturation should be higher because your peak current, it will be much bigger into the inductance like expected. How to calculate the volt microsecond product, it's also given in, if you look on the inductance versus current graph, and when the inductance drops to the level when it starts to be totally saturated, at that value, if you LRS multiply by this E max, you will get the volt microsecond product. And for the safety reason, you should consider some security factor for iron powder, alloys, superflux based inductors. You can take this like it is with a factor 1. For inductance by ferrite based, you should use 0.7, so 70% maximum of that. DC resistance, of course, this is dependence of the wire thickness. It's the wire thickness and the wire length define the DC resistance, measured again at 20 degrees Celsius laboratory condition, not floated with fluid nitrogen to make it as like a superconductor, because it makes no sense. You will not have this condition in your DC-DC converter as well. So they consider that it is measured at laboratory condition, and the maximum definition, it is always, which you will never get actually a piece which reach that value. The self-resonant frequency is also very important to take attention, that the self-resonant frequency must be much more higher like the switching frequency. If you look on this impedance characteristic of the inductance, sometimes you may have the problem that some manufacturer give linear impedance scale, other one is in logarithmic impedance scale. You can see here the comparison, it's both only just the different scaling. And if the self-resonant frequency of this inductor is 20 megahertz, I will say I will use maximum 10% of the SRF. So I will say 2 megahertz will be my maximum switching frequency where I would use this inductance. In this area, it's already too dangerous because that drifting also from lot to lot a little bit, because the capacity of the wire could change, and also it is too risky that the inductance will be have different value. The high voltage is also important. Standard inductors can be used only to maximum 80 volt. That's the peak of the standard version. Cannot be used for offline, because you have a high voltage applying to the inductor himself. And for high version, please use our high version defined inductance, because we are using a better isolation for the wire. We have a winding testing process which is unique. Only Würth Elektronik use that. We have defined the own standard. You can get this standard from our website, because if you use a very high voltage, it's very important that the inductance doesn't have a short from winding to winding. If you use this 300 or 400 volts, like an offline converter, you may have this drop over the inductor, this voltage, it is on the inductor. If you use the inductor just for a filter, then you don't have to take care for a high voltage, because in a filter application, the voltage is applied to the capacity of both the inductance. You will never have this high voltage. If you store energy into the inductance, you may have this switch here instead of this capacity, and then you will have this exactly the 400 volt on the inductance, and then you will need the high voltage. For filter, not. Additional, it's very important to take care for the maximum operating temperature, because the maximum operating temperature, it is the ambient temperature plus the self-heating of the inductance. So if you have an ambient temperature of 100 degrees Celsius, you may have to use a derating of the maximum nominal current, because you can apply only in this curve showing only 60% of the maximum current capability of the inductance, because it is above 85 degrees Celsius and then plus 60% of the maximum current. At 85 degrees Celsius, you can use the maximum current, because 40 Kelvin plus 85 degrees Celsius is 125, and then it's safe and it can be operated. Well, this losses is giving from the total losses, actually is giving from the DC losses and AC losses. So if you have an inductance which is not getting too hot, it's automatically good for efficiency, because you're not losing energy and you have less effort to cool the system down. The inductance losses can be a little bit tricky because you may have on one side the copper losses and other side the AC losses. And the AC losses can be current from eddy currents, which is generating the core, some hysteresis losses, but also skin effect and proximity effect. By the wire, you can use a trick that instead of using a standard round wire, use kind of Litz wire or flat wire, especially when you're using higher switching frequency. A flat wire is much better because you have the skin depth not so deep into the copper, so it might be much better if you use a flat core wire for high currents. This is by the skin effect. Of course, you have this different frequency where you can have this intrusion of the current into the wire. And by proximity effect, it depends on the winding structure, how you do this inductance to try to avoid this kind of proximity effects. The next point is the core losses. The core losses can be calculated by using the Steinmetz formula. The Steinmetz formula have a good approach until 50% duty cycle. As soon you are going away from the 50% duty cycle, you have to consider this error factor. And that's the problem, but mostly the Steinmetz is not more so valid or not more so accurate. Additional, the Steinmetz core formulas, which is when you're giving these core losses, it's always measured with the toroidal core and using a sinus wave. And the sinus wave passing completely a full BH loop, which is actually not happening in a DC-DC converter. Because of this reason, we decide a different approach to use core losses and not using a sinus wave, and not only to be accurate at 50% duty cycle, which is the most acceptable accuracy. For other duty cycle, you can almost forget to approach the Steinmetz. We made a very simple class D amplifier, D-class amplifier, and we start to measure the power before the inductance, applying a square signal, and then measure the power after the inductance, and the difference between these two power, what was the AC losses. The DC losses can be very easy calculated according to the RDC of the wires, and the AC losses, which is core losses and proximity losses, it is actually the real losses which happen into the core. With our simplified formula and with our approach, where you can see in this rectangle signal, we are using a BH loop exactly in the area where it's happening in a DC-DC converter as well. We can say that our accuracy is quite very good, and the highest accuracy with a very wide DC range, because you can use this approach with a rectangle signal much better, like a Steinmetz method. Additional, we can consider different core shapes. We can consider also these fringing effects of the air gaps, the winding structure. We can measure iron powder cores, different core materials together in the same core, in the same structure, and it's not considering only ring cores like Steinmetz are doing. Where to find these values is very simple. If you go to our website and you click on the REDEXPERT button, we have this online tool where you can calculate your inductance for buck boost SAPI converter, and you can already see the real losses of the DC and the real measured losses of the AC losses of this inductance. All these values which you will find in the REDEXPERT are really measured value. Additionally, you can even approach, according to these losses, the total losses, you can even approach and you can consider how much you can expect the self-seating of this inductance, and you can consider if this is enough or too much maybe for your application. REDEXPERT is the link here, vonline.de or .com/REDEXPERT. Automatically start the software. It's an online tool, and if you register by yourself, you may have also a possibility to apply more filter, and you can compare more components, and you can put more cursors in the same time. I think this is right now the world's most accurate AC loss model which we are using in the REDEXPERT, because it's unique, and you will see that it's quite very interesting when you are making your DC-DC converter, because all this value we did measure with the infrared camera. It's quite very cool that you will see that it's even less, because you have some seals heating conductive PCB, or you have some emission of the heating, and you have even less like you did expect. Now, about EMC input filter. First of all, I want to say that it's very important when you are using an inductor for storage, you should always choose a shielded inductor. The unshielded inductor, it's like a bobine core on the PCB 90 degree, like a small antenna for emission. And you will see that this shielding, it's quite very important when you go to the EMC chamber and you realize that the unshielded version have a high emission and the shielded version have in a far field low emission. This is for radiated emission measurement. But already on the conductor emission, you can see sometimes this improvement. I will give you here an example from a customer who did measure it with a rod-con inductance, and he did not pass the conductor emissions from 150 kilohertz to 30 megahertz after he changed to our shielded inductance. And we tell him, please float this area also with the PCB with ground plane. It was a double-side PCB. He reached just a little bit noise above the noise floor. Even the EMC guy was very impressed, and he did say, I did not believe that the green color, it is so better, much better like the yellow color for the EMC because of the changing of the color of the PCB. Of course, this was more like a joke, but it was really impressive what can be improved with using a shielded inductor and some better shielding on the PCB using these floating grounds. Another point which I want to point out, which is also a point, a dot actually on the marking on the inductor. If you consider all our inductance have always this mark in this small dot, which means the beginning of the winding of the inductance. In fact, the inductance doesn't have a direction. It's not like a diode. But we point with this dot that this is the beginning of the inductance. It means this is the first wire close as possible to the core. And this dot should always look to the switch node, because this making in terms of EMI much better, because the self-shielding of this winding could also help in case of some E-field emission for the inductance which can occur by the DC-DC converter. And sometimes it is also interesting to see, we had some experience where customers say our inductance make audio noise. Even we are switching at 500 kilohertz, we can hear some noise. Of course, you don't hear the 500 kilohertz, but you hear some harmonics. After we change the direction of the inductance, so turn the inductance 180 degree, so the dot to the switching node, the noise was disappearing. Maybe disappearing from the audio area where we can hear it, but anyway, it was a nice experience, and because of that, we recommend to put this dot to the IC, direction to the IC, and especially keep this track short as possible between switching node and inductance as well. This is also good for EMI. Some additional information you can get from us. We have some nice books, already 5 different books. LT Spice book, Trilogy of Magnetics, Trilogy of Connectors, ABC for power modules and for capacitors. If you don't own this kind of book, please ask our sales people for sales engineers, and they will provide you, or you can order that also from our website. The Trilogy of Magnetics is already the 4th edition, and it's a good description of how to build different filters, and it's trilogy because they have 3 parts. One part is describing the components, and another give you also some directly application. If you still have question, now I will start to answer. Let me see if some questions have been asked. Okay, somebody did ask what is the difference between nickel zinc and manganesic zinc. Well, the big difference, both are sintered material, but both are black. The only one thing, you will see that always the manganesic zinc have a coating. A coating means that this material is conductive. If you want to find out and you don't have a magnetic analyzer at your desk, but you have a multimeter, it's quite very easy to find out with a multimeter. If you apply the multimeter with the probes on the surface, very close the probes to each other, on the nickel zinc material, you will not measure any DC resistance. On the manganesic zinc, you will see a resistance something like hundreds of kilo ohms, because the manganesic zinc is high conductive. That's the reason we have to coat them. So it's very simple to find out nickel zinc, manganesic zinc. If it's not coated, even on both black, one is conductive, the nickel zinc is almost not conductive at all. Let me see some other questions. Somebody asked here about, I need my glasses. Volt microsecond product. Could you repeat how to use them for choosing the inductor? Don't remember the slide number. Okay, it was the maximum saturation point of the inductance. So if you look to the graph, inductance versus current, you will see that when the inductance totally saturate, it will remain inductance value like if it was before something like 100 microhenry, and the rest of the inductance, it is 5 microhenry. And at that point, when the inductance start to be linear, it is this current. If you take this L rest multiplied by this current, this is the maximum volt microsecond product. Multiplied by 0.7 for a security factor to be safe. Somebody asked another question. I need to use a 1000 volt flyback transformer. Okay. Nice to hear that you want to have a 1000 volt flyback transformer. In this webinar we talk about inductor selection, but if you apply this question to my colleague in salespeople, we have local salespeople in Turkey, and you can apply this question to them and they can provide you a custom specific transformer for that. Another question. Do our model in LT-SPICE include all the heavy REDEXPERT program? No, in LT-SPICE it's only just LT-SPICE replacement circuits models, and they are not containing the core losses. What we have in LT-SPICE, we have some ferrite beads where you can consider the DC bias pre-saturation, but core losses are not included, in fact, in the LT-SPICE. Another question. Could you give any comments of the parallel parasitic capacitance of the inductant? It's a physical capacitance, so it's also dependency related to the complex parameter core materials. The parallel parasitic capacitance is given mostly only just by the winding method, or the winding, how it is made the winding, because this wire winding, it's making this capacity, and as soon you have less turns, you have less capacity. As soon you have a very small bobbin core and you have to put a lot of wire, you will have a higher capacity and automatically a lower self-resonant frequency. But it not depends on the permeability on the core material. Okay, you can say yes, it depends some way, because if the permeability is very high, you will need less number of turns, but the number of turns actually are the manufacturing this parasitic capacitance. Okay, I have to mention additional, my colleague Eleni already mentioned this presentation. It is recorded and it will be available on the website. Just go to our website and you will be able to download it, including my voice. I will not listen again because I don't like to hear my voice myself. So I guess our time is quite over. We did plan with 30 minutes and 15 minutes question and answer. The most important thing is when you're doing some calculation or choosing the right inductance, what I can tell you from my experience is don't give up. It's always a possible solution. Just you have to find out the right way. It's always a solution. Never give up. If you call us or you mail us, we have also a possibility to give you some ideas, and we try to help you. We have field application engineers worldwide, locally situated, and we can try to give you our best for choosing the right products. If you want to keep in touch with me, I am also on Twitter. We will see also on LinkedIn. I have an account on LinkedIn, also a landing page, vaonline.com/asklaurent, or contact me directly on this asklaurent@vaonline.com, and I will try to give your best answer. And for the question which was not possible to answer right now, I will answer privately in direct, because when you register you put an email address and I will reply to this email address. Hope you enjoy it and you have fun, and see you next time. So now I will mute the presentation. Thank you. Bye bye.